Good morning, guys. So you may have noticed that we did not have so many videos last week. In fact, we had none, and there's several reasons to that. So I kind of want to talk you through, and also to give some plans for the future of this channel. So the reason why I don't have time to record full-time screen contests is because I'm doing something else full time and that is working. So yeah, it is sometimes kind of challenging to find a consecutive chunks of 3 or 4 hours to participate in a contest, to post process a video, to create a thumbnail, stuff like that. What I can do, however, is record something shorter. So I more or less consistently have several 3 hours every day, but it's not 3, 4, 5 hours in a consecutive manner. So what I wanted to do instead today is show you one problem, just one, not like 7, as you usually see in the screencast, which I was solving today. In fact, which I was solving yesterday. I found it very interesting. It's a 2700 rated problem from a recent Harbor Space contest. Harbor Space is, of course, the company that kind of helps with organizing and sponsorship of educational rounds. But this one was kind of global, I guess, because it's Div1 plus Div2. So what I want to achieve by switching to this new format of explaining just one problem but in greater detail is that sometimes when I'm in the screencast, I don't have time to walk through all the little details, and that kind of harms the quality of the content. Instead, here I can focus deeply, and in case a problem has non-trivial ideas, we'll walk through them one by one. So hopefully that will help in understanding. And I also wanted to pick something challenging for myself for the first such attempt. So I picked 2700 rated problem. As you can see, it took me quite some time to understand my mistakes. But yeah, that was solved. So the problem goes as follows. We have several distant integers, a1 through an. Each represents a node of a graph. So there is an edge between two nodes if the two values are not coprime. So hopefully you know that numbers a and b, they can be coprime, they can be not coprime. That all depends on their greatest common divisor. So as they conveniently remind us, the numbers a and b are not coprime if their greatest common divisor is greater than 1. And what they want us to do, they want us to ask Q queries of the following type. So in this query, we want to get from one given node AS to another AT. So there's a starting node and a terminal node, I guess. In order to achieve that, we can choose an existing value AI and create a new value, an plus 1, because we had n vertices already, and we create an plus 1, which is AI times 1 plus AI. And of course we add new edges from this vertex to all vertices that are not coprime with that. Obviously n also gets increased by 1, so that you don't get duplicate edges actually, vertices. We can repeat that operation multiple times, I don't know, insert 1 billion vertices or something like that. The values can overflow, they may not fit into 32 bits, 64 bits, whatever you want. So there is no limit on values that new vertices can have. We want to know what is the minimum possible number of newly created nodes so that AT becomes reachable from AS. And there's some info description here. So like you have roughly 10 to the 5th nodes, roughly 10 to the 5th squares. Time limit is kind of increased from the regular 2 seconds. The second, like there is an array, values are not that large, which is important. Then the description of the query as follows. So what is interesting about this problem is that all the components are fairly simple. So like, I was more or less able to figure out each one of them on its own. I believe like if you had a problem that uses one of those ideas, it would be around 1800 rated. So like a good candidate master should solve them always. But when you combine several simple ideas, that becomes quite interesting. I don't know. Like the problem becomes harder, but it does not become like harder in a dumb way. For example, it's not hard because it uses like, I don't know, not widely known data structure or anything like that. It's just a combination of simple ideas that makes a beautiful problem, in my opinion. And to be honest, when I started solving this, I was kind of solving it for practice only, but then I realized just how much you can gain from solving one 2700 rated problem. And I kind of saw that, you know, this problem is worth a video on. So, when faced with a problem like that may sound very challenging, because like, what are you gonna do? We may want to create the graph explicitly, right? But when you try to do that, you will quickly run into problems. For example, the size of the graph is, of course, linear in number of vertices plus number of edges, right? And like number of vertices is n, and we kind of don't care about that one because that's relatively okay for graphs. Yeah, 100,000 vertices, why not? What is not okay is the number of edges. When trying to bound number of edges, you want to think like how many pairs of integers can be not coprime. And the reality is that every pair of vertices can be connected by an edge, because let's say all numbers, all ai, so like for all I from 1 to n, it may be the case that ai is divisible by 2. So 2 divides ai, and then all aij are connected in the graph. So like that's an edge. That's an edge. And that of course means that number of edges can be up to n squared, which makes it unrealistic to model the graph as is. So like we can't even generate the graph, and they want us to add new vertices and edges. So what's going on? Typically, in such cases, there is some structure to the graph that we overlooked. When the original graph is too large to fit in memory, you almost always can reduce the number of edges very significantly, because most probably you will care only about things that are connected or are not connected. For example, like this problem specifically asks us about like how many new vertices it will take to connect two vertices. So one obvious particular case of that, a special case, is when vertices are already connected, you kind of don't care, right? Like you don't care in a way that you don't need to add any new vertices whatsoever to connect to vertices that are already connected. So that obviously leads us to think about connected components. Connected components on their own are kind of simple, right? There's not much to them. And there are various ways to implement connected components. We will need still to reduce somehow the number of edges that we want to use in our connected components. But other than that, connected components are fairly simple. So one of our ideas will be connected components. Let me straighten that up. Connected components can be found in various ways. The way I personally prefer is disjoint set union, partially because probably you have disjoint set union priority, and also because I don't know. I just find it simpler to understand, and also it's semi-dynamic. So, for example, if the queries were not independent, then we may want to keep the edges that we add. So that would not be possible if our connected components were found with a DFS, BFS, whatever. But it is possible if our connected components are stored in disjoint set union. Now, in case you don't know how disjoint set union works for connected components, I will briefly explain that. In case you do know, you may skip this part of the video. There will be some timestamps in the description to let you jump to the more interesting part for you. So originally when finding connected components with DSU, we kind of create one component for each vertex, that is how things are. Then we start adding edges. So when we add 1, 2, we kind of say okay, you know what? We'll keep a representative of each component. It may be any of them, right? But we want each component to have a representative. Partially because, usually, or not always, but sometimes when you find connected components, you want to compress the resulting graph. And one implicit way to do that is to have representatives. So, we may say that there is vertex 1 is a parent of vertex 2. And then whenever we ask about vertex 2, how to connect to it, it's the same as connecting to the vertex 1. If we just speak in numbers here, if we just speak in graph theory and not specific conditions here. So that may be useful. So we started in edges and we say that one of the vertices that we connected is the parent of another one. So your normal disjoint set union, they say okay, you're the parent of this vertex, you're the parent of this vertex. Sometimes, however, when we take 2 and 3, it would be ugly to say that 2 is a parent of 3, because then our structure, we have a connected components with 2 representatives, with 2 roots, which is not good. Not good. 2 roots is not good, right? Good. I suppose has only 1 root. So yeah. So instead of just merging those guys, connecting them with a parentage, we always find representatives of components. So when that's your normal merge on these. You want to merge parents of components. So here, for example, we may have added edge from 4 to 1, and we only have 1 root, 4, which goes to 3, 1, 2. And yeah, and whenever we find root, you may apply your whenever we call find on DSU, you apply your path compression heuristic. Whenever we merge, you decide which way the edge goes based on rank heuristic. So like each vertex has its height in the tree, and we try to keep heights more or less balanced in a way that height of each vertex is greater than height of all its children. And whenever we merge, we make the one with the highest rank root. If you're interested in specific analysis of performance of the issue, I'm pretty confident that you can find it somewhere on like cpalgorithms.com. So yeah. Now, suppose that we kind of found connected components with this approach. So like you just, for every edge, you merge two components that you currently have, that the vertices that you're trying to connect currently belong to. All right, so we have some connected components. In fact, we don't have them yet. Why? Because there are too many edges. There are just too many edges. That's too much. So now you want to start thinking about specific structure of the edges. So like you connect two vertices only if they have a common divisor, right? So one common technique in such cases is, well, you can do something by looping over numbers, and you can do more or less and then looping over their divisors, or you can do something by looping over prime divisors and then looping over numbers that are divisible by those divisors. So you can have two ways. So for AI in A, then you have for divisor in divisors of AI, right? Sorry about that. Or you can switch those two around and you say like, okay, I'm going to loop for prime number in a set of primes. And then you say like for AI such that, well, for AI, but you don't loop over the entire array A specifically. You like sort of have a helpful structure. So it's like in, I don't know, map of that prime or set of that prime. So like these loops are all numbers that are divisible by P. And regardless of which one you choose, you will most likely need to factor numbers quickly. If you start thinking about it, you may need to factor that many numbers that are up to such. And it's a big question whether factoring them in square roots of maximum value will work. Because now it's 10 to the third times 10 to the fifth, but the constant is quite large, so it's 10 to the 8th, but then you have a large constant. The problem that is not the... I have not tried submitting with naive factoring, but usually when you have such situation, like you don't have that many numbers, you can factor them in a more efficient way, which of course involves sieve. So that's our second idea, that we must probably need sieve. So what we'll do is we'll call sieve of like, I don't know, maximum value that we can ever have. Then we can factor numbers quickly because of two reasons. So first, sieve can just record instead of recording whether the number is prime or like is not prime. the sieve can record the largest or some prime factor, right? So like your normal sieve goes something like this. You have your array is prime. You say, okay, I'm going to loop for d from 2 to square root of maximum value. And you say, like, if d is prime, then you can loop over multipliers. The way I usually do it is I loop over from d square up to m with a step of d. So like plus equals d. And then you select is prime of multiplier is false. Instead of doing that, you can have an array of prime divisors. And here you can assign d. So you know that d is a divisor and it's also a prime divisor. So by doing this, you will be able to quickly factor all numbers by starting at mth index of the array, and you look at this value, you see that it's d, so you know that d is a prime divisor of m, and you can quickly divide. So in fact, you will divide in log n time. So yeah, you factor all numbers in logarithmic time. Now the way I did it was a bit different, so there was no specific reason to that. I believe that this way of factoring is the fastest. But I did it kind of differently. So actually I may want to change the implementation before I show it to you. Because this one is just objectively better. Yeah, I probably will. Okay. But still, like, either way we need sieve. No matter how we factor with it, we need sieve. So hopefully sieve is not something new for you. But again, you can read about like it on cp-algorithms.com. Hopefully it's up and running. If not, then you can just Google, right? Sieve of Eratosthenes, a famous Greek mathematician from the previous era, I guess. So yeah. So by using sieve, we can quickly factor all numbers. Now what we can do with this information, our idea was that for each prime, we wanted, like, each prime gives birth to some components, not necessarily the same as the resulting component. So here may be a component of number 3, here may be a component of number 5, and then here may be a component of number 7 or like 11, and they combined give one component of the resulting graph. So yeah. And why we can just use primes? That's an interesting question that you may have asked yourself. Well, because it kind of, in a way, it doesn't make sense to have GCD equal to 6. If GCD is equal to 6, let's say, then it's already divisible by 2 and 3. Like A and B have, if they have a common divisor, then they obviously have a common prime divisor. So in a way, we don't care about divisors that are not prime. And that's why we can, in particular, like loop over prime divisors only in logarithmic time, and not over all divisors in square root time. So okay, if we know all numbers that are divisible by 3, or all numbers that are divisible by 5, and all numbers that are divisible by 11, how do we create such components? Like, what edges we need to add to ensure that when we merge them in DSU, they will give this component. So one way is, of course, add all edges between all vertices that are divisible by 3. This is, of course, inefficient. We already talked about that, because the number of edges can be quadratic. Another way is that which is kind of common, you find some chain. Like, you order vertices that are divisible by 3 in some specific way, which is arbitrary, but like you fix the way. Then you connect neighbors, and obviously in this way you achieve the same in terms of connected components as connecting like everyone with everyone. Then you have another chain of numbers divisible by 5. Then you have another chain of numbers divisible by 11. They may intersect at multiple points. They may intersect along some path that's not relevant to our problem. The point is that like they intersect because there is a number that is divisible by both 5 and 11. There is a number that is divisible by both 3 and 5. And it stays this way. So it is somewhere in the chain. So by using some subset of those chains, we are able to get from each place to each place. One possible example is subway lines. Like, we don't need a system to directly connect each pair of stations on the same line, right? They are connected in a line, and well, sometimes they are connected in a circle, but let's ignore that fact for now. So yeah, you just go to the neighboring station, and eventually you get where you want it. So in terms of connected components, that's the same. And that greatly reduces the number of edges. Obviously now the number of edges is more or less of n log n, because each number has log prime divisors at most. And yeah, this resultant graph has as many vertices as there are pairs P in AI, such that P divides AI and P is prime. So of n log n. In the worst case, well, potentially we may get lucky, and then there will be fewer edges, but like, who cares? N log n edges is fine for such constraints. Also, these you merges in more or less constant size, so it's acceptable. It's acceptable. So we finally computed our connected components. What do we do about them now? We want to start adding edges. So all of this time we spend just not caring about adding edges at all, just like doing something that will definitely be useful. Then we kind of understand that we don't know anything about adding edges. Like, adding edges will connect to previous vertices in some way, right? Vertices are connected via prime divisors. So we want to focus on what are the new prime divisors of this number. One interesting thing is that this is co-prime with that, but we'll see if we can use it somehow. Now, after doing all of that, I actually looked at the samples. And one thing that I immediately noticed is that the answers are mostly zeros and ones. So for zeros, we already know why, because they are already in the same connected component. For ones, I guess that there will be a way to determine them. And then there was a singular tool. So obviously, if the answer could be only 0 and 1, we could check if it's 0 with DSU and then just output 1. But here, apparently, they say that the answer can be 2. But still, maybe we can limit somehow the answer to this question. Uh, so after wasting 15 minutes or so on considering this, like the fact that those two are prime, I stumbled upon the fact that, well, the answer is always small, and this is one more thing that you want to look for. That is a recurring idea in most problems. So like, if you know that answer is small, then you can kind of cheat by not finding the specific answer, but rather, I don't know, rather just checking how small the answer is. So like, we already know how to check if the answer is 0. If we devise a way to check if the answer is 1, then we can output 2 in all the other cases. So answer is small is another idea. And here the answer is small because if you take any two numbers, 3 and 5 or whatever, but 3 and 5 are the numbers that they used down there. Oh no, actually the numbers they used, like those are indices, so the numbers they used were 7 and 25. So we, basically this has a prime factor of 7, this has a prime factor of 5. So another way of thinking about it is like we want to connect two prime divisors, actually. Instead of connecting vertices, we want to connect two prime divisors. Also, another way of thinking about those things is like, instead of having a vertex for every element, elements are kind of useless. So we instead have a vertex for each prime divisor. Then we connect them. So like those numbers that have 3 and 5 as common divisors, like they are divisible by both 3 and 5, they induce an edge between all numbers divisible by 3 and all numbers divisible by 5. Also those numbers induce this edge. So not only we don't have quadratic number of edges, we also greatly reduce the number of vertices in our graph. So like if we just create a graph where vertex is a prime number, that is up to 1 million, then there will be approximately like 50,000 vertices, so like 3 times. It's not a massive help, but I guess it helps a bit. I have not tested what happens if you keep the graph on original numbers. I guess you will get at least like 3 times penalty, which may be still acceptable because this submission, it works like in approximately 1 second out of 4 allowed, so maybe, who knows. So another idea is to change the graph so that it's more suited to your problem. So the exact graph may not be obvious. So like there is one very obvious graph and we just connect vertices. And then there is another graph which is kind of better suited. But I guess this, I don't want to make a claim that it was not critical in this problem, but it surely helps if you just can have one vertex for each prime and then connect primes. But getting back to the example of 7 and 25, you may start wondering, like, well, what exactly am I getting? Like, how do I connect 7 and 5? How do I connect 7 and 5? I mean, say, okay, like, if we take 7 and we use this, then we will connect it with 8. So, yeah. 8 only has divisors of 2, so at the cost of 1 we can add edge between 7 and 2, and in the cost of 1 we can add edges from 5 to 26, specifically to 2 and 13. So you get this and then this. And here just realize, well, wait a second, like I have edges that go to vertex of 2. And then hopefully you realize that if at the cost of 1 you can connect any number to, at the cost of at most 1 you can connect any number to 2. Because if AI is even, then it's already connected to 2. If AI is even, then all prime divisors of AI are already connected to 2. If AI is odd, then 1 plus AI is even, and the cost of 1 you can connect them. So in this way you get that answer is always at most 2 if you go through 2. So great. Now the only thing that remains, like we already talked how to determine whether the answer is 0. Just use your GSU, check if find of some prime divisor of AS is equal to find of some prime divisor of AT. Doesn't make sense to check all pairs of divisors because, well, like you already have what you want to. So now we want to understand which edges specifically we can add at the cost of 1. And here I was wrong for quite a long time. So it turns out that, like, well, obviously you can add edges between all factors of AI and all factors of AI plus 1 at the cost of 1. So like I said, okay, I will factor this, I will factor this. Each one of them has off log divisors, so in overall I create log squared edges, I guess, of cost 1. This is important that they are of cost 1. And then times q, well, that is okay. Because like log is an upper bound. If you start writing explicit figures, then I assume that it will be a bit smaller, given that this is AI plus 1 is not in the index, it's just like regular plus 1. Just so AI is an index, and then plus 1 is just plus 1. So like, whereas just one number can have log divisors, then 2 consecutive numbers have log square pairs of divisors, well, that does not happen that often. Alright, so that is kind of possible. But the thing that I was wrong about is that there is also an edge of length 1 between each pair of divisors of AI plus 1. Yeah, that is non-trivial observation. How it comes to be, like, I believe that there was some example that I found. I can't remember it exactly, but like it might be the case that you want to connect number here, some prime divisor p1 here, with some number here, and you don't connect them by adding two edges of length 1, of cost 1, but you instead connect them by saying, okay, I have AI here, I found P3 here, but also AI plus 1. It is divisible by P2 and P3. So what it means, by adding one vertex, you added both edges. So like each edge is kind of of cost 1, but like they are added at the same time. So what you should instead do is add different edges. Or maybe I'm actually wrong, right? Yeah, I'm wrong. I formulated it wrong. So we want to connect P1 with P2, and the way to do it is we take a different vertex AI that is not here, and it turns out that P1, P2 divides AI plus 1. Plus 1 is again not in the index. So yeah, it's not true that AI is divisible by any of them, but this AI plus 1 adds this edge, because it creates a node that is divisible by both, and in our definition, two primes are connected when there is a node divisible by both of them. So yeah, those edges are also important to count. And there's also a log squared number of them. So yeah. Now once you have all edges of length 1, you can just check whether two vertices are connected by one such edge, and then you get to know whether the answer is 1 or not. So like to check that answer is 0, you take your DSU and check that they are in the same component by calling find 2 times. Or maybe your merge returns a boolean denoting whether the components were different, then you can call merge. Then to check 1, you take your prime graph explicit, built from those edges for all EIs, and then everything else, the answer is 2. And we can in fact even like provide specific answer. The answer is 2 when like, we can restore the path, which is like of course going to 2 just twice. So yeah. And that's more or less what I did. And you may see that all of those ideas on their own, they are not too difficult, right? Like I bet that we all could figure that out with enough time. Like connected components, okay, easy. Sieve, right, acceptable. Answer is small, yes, like just looking at the samples and then thinking a little bit. Change the graph, well, maybe not, but at some point, like I change the graph maybe in 2000 idea, 2000 rated, I mean, on its own. But at some point you also learn to see such things when like the graph that you are trying to use is not very well suited. It has like necessary vertices, stuff like that. So it may be simpler just to have the graph off, like just to change the structure of the graph. So yeah, overall that's what I did. That's what I did. Give me just a second to change my implementation a bit, so that it factors numbers in the way that it should factor them. And I will be right back. So just a quick break, because like I believe that my sieve is not optimal at the moment. Alright, so coming back to the implementation part, you may have a sieve that looks something like this. So you have your vector of prime divisors and you loop, and here you fill it this way instead of just setting this to false. And you also compare the number is prime if it's equal to its prime divisor. Yeah, same here. And you return a pair of like prime divisors and primes in case you need primes explicitly. Then you have your DSU, which is kind of simple. Size, parent, rank, you know the drill. Like find uses path compression, merge uses rank heuristic to determine who is going to be the roots, and also fixes the ranks in case they should be fixed. So the way we do it, we call sieve from like the maximum number that we want to factor is 1,000,001, which is 1,000,000 plus 1, AI plus 1, if you remember. So in the way I write sieve, it kind of does not factor the maximum number, it goes up to n, because like just having less equals here, then also n plus 1 here is a bit annoying. So I just add 1 here once. Then we can factor numbers quickly just by such loop. So while n is greater than 1, we take its prime divisor, we push it back to its factors, and we divide n by this divisor. Then I created a map that like we kind of have primes, which we, to be honest, want to enumerate, but there is no enumerate in C++. So yeah, this trick usually enumerates things. So like for each prime, we know its index in the inputs in the list of primes. What it lets us do is like we factor AI. We connect adjacent factors, again, not, well, we could create log square edges, but they're why, just why we want to do that. So once again, this chaining technique presumably helps here. Then we can have a G, and because we want to quickly check whether it contains an edge, I opted to have an ordered set here. So what we do is for all AIs, we want to connect all factors of AI with all factors of AI plus 1. And notice that here we can't use the same chaining technique, I believe, because it's important that all edges have a weight of 1. So connecting two edges of weight of 1 does not give you an edge of weight 1, it gives you an edge of weight 2. So you can't just change everything to such chains. And then we also connect all factors of AI plus 1. The way I do it is obviously inefficient in a way that like here you actually like I loop over this F1 and F2 and also over F2 and F1 in two ways, but like it's constant term. If you got chill, you may needed to optimize it, but this is also fine. And also you may have noticed that I just explicitly take well, first thing I do is I have factor, I have a prime divisor. I want to find its index, so it, like we enumerated primes so that we can use their indices as indices in the graph. But also I want to call these uFind. Because I want to connect representatives so that I can check representatives and not check the entire component. So yeah, after I added those edges, so like this part is like building the new graph. This part also in a way contributes to this building new graph. And we just process squares, it's rather easy, like you want to make sure that your indices are 0-based, then you factor AS, in fact, to be honest, that is of course very inefficient of me. You just want to take one prime divisor, of course. So if you let me go ahead and submit this to code forces, one second. Yeah, let me bring this back actually, because yeah, that just entire screen now. Problem set. Oh, that's so slow. It's so slow. Where is it? It's somewhere here, right? Yeah, you just want some prime divisor of AS and AT. You want to, well, of course, convert them to indices in the list of primes and also call these uFind so that you work with representatives. Well, it's surprisingly it's not much quicker, because I assume that the most complexity comes from the fact that we have log squared here and not like log instead of O of 1 here. So yeah, and then I just check if the vertices are the same, so representatives are the same, then it's the same connected component. If this contains an edge going here, or this contains the edge going here, which I believe is never executed. Like it's the same thing as this, but just for the sake of symmetry, I wrote both. And the answer is 1. Otherwise, the answer is 2. And most of the time, I was figuring out this part. And I found some test case. Yeah, like if you're stuck on something, well, it was practice, so I kind of did not care about running submissions. But to be honest, you should, because like it makes you think what I did wrong and what should be changed in the code. Like eventually I realized this mistake that I can connect by using a different vertex that is not related to neither P1 nor P2. And yeah, I had to do this thing. So yeah, this was a very nice problem. It's 2700 rated, but as you hopefully have seen, like all ideas are very reasonable. Implementation is rather simple. The only non-trivial ideas come here when we change the graph, and then everything else is something you may want to learn in case you don't know about DSU, connected components, errata span sieves, quick factoring with sieve, just stuff like that. Be sure to check them out. They will greatly help you to improve on a bit lower levels as well. Not only like 2700, so Grandmaster level. International Grandmaster, in fact. But yeah, I really enjoyed solving this problem. And hopefully, so this is it for the problem. And now we come to plans on the channel. So hopefully this was interesting enough for you and also educational, because like when we have only one problem, I can focus very in depth on it. So I don't know how much I spent, probably like an hour already explaining everything. But hopefully I was able to like delve deep into all ideas. So, and I like, in my mind, it should be very educational. And by using higher rated problems, I can like cover several topics so that hopefully everyone can find something interesting for them. And also for me personally, just a great way of training, because I mostly don't solve such problems, whereas this problem shows that I could. I could solve them in contest as well if I get some practice, because there were no ideas that I did not know, and hopefully there were no ideas that you didn't know, except for maybe that changing the graph thing. But yeah, like, I just think that this format can give so much better. So first, videos become shorter, so easier to film. Videos become shorter, so easier to watch, because like, let's be real, to watch a entirely 3-hour screencast, it's kind of challenging, because you mostly want to find the solution to one problem. One problem means in-depth explanations. It's better for my training to solve higher rated problems. So I only see upsides. I don't exactly see downsides. So probably I will try to work like, maybe this will become a daily thing actually, like, because if I only need to spend 1 hour in the morning, then it's easy, right? Much easier than spending 3 hours in the evening, like after a potential long day at work. So yeah, let's go. Let's try and make this a daily thing, I guess. Hopefully you learned a lot. So if you got questions about that, you can ask me in the comments down below, or you can join my Discord server, which is a recommended way of asking questions. I try to check it out from time to time. Like previous week I was very busy, so in case you were wondering where I am, so that's where. But this week, I will not be that busy to film videos like in the morning, like your daily, I guess, dose of competitive programming. So yeah, with that in mind, I'll see you hopefully tomorrow, and you may see me earlier if you join my Discord server and just hang out there. So see you all guys, bye bye.